Hi, it's Moser with a quick tutorial on ionic compounds containing transition metals, actually using the stock system. After this video, you should be able to take any compound that contains a transition metal and name it. You should also be able to write the formula for any ionic compound that contains a transition metal when you're given the name. You already need to know anions from cations, the ions that are made by the common main group elements, how to write compound names and formulas for basic simple binary monatomic ionic compounds, as well as what transition metals are and how to find them on the periodic table might be useful. Okay, let's get started. Before we do, please make sure you've got a periodic table handy and one of these, the ion and oxidation number reference sheet. You'll find it in the folder, in the Chapter 7 folders, and it's linked on the Chapter 7 plan, but make sure you grab one. Okay, so you've seen this slide before. We're talking about naming ions, naming monatomic ions to be specific. And we've already talked about the main group cations and anions. Now we're interested in the D block elements, because the D block, well, it does some weird stuff. Remember that the D block elements have delocalized electrons. That's what gives us the amazing characteristics of metals through the joys of metallic bonding. Well, because of the fact that they have those delocalized electrons, something else can happen. Transition metals sometimes make more than one ion. We know that oxygen generally makes a -2, and sodium always makes a +1. Fluorine always makes a -1. Those are easy. But with the D block, each element can actually form multiple ions. And there are some patterns. We know which ones generally form. But you'll need a reference sheet. That's that reference sheet I told you to get. Because of the fact that these elements make different ions, we have to specify which ion appears in any compound. So we use Roman numerals, like this, in parentheses to designate which ion we're talking about. Fe2+ is iron 2, Fe3+ is iron 3, and the Roman numeral tells you what the charge on the cation is. When we have a compound made with a transition element, when we name the compound, we have to specify which ion we're looking at. There are a few metals that don't form more than one cation, and they don't need a Roman numeral to designate them. Silver's one that comes to mind. It always forms a +1. There are some others that we'll talk about as we come to them. So we'll start off with formula writing, and we'll start practicing with iron 2 oxide. Well, just like when we're naming simple binary monatomic ionic compounds, we write down our ions. Well, oxide's easy. It's O2-, iron 2. Well, it's Fe. What's the charge on it? Right, 2+. And the thing that tells us that is the Roman numeral in the parentheses after the word iron. So now we have our ions. How do we go about writing the formula? You probably already knew this and didn't need to do any fancy pants algebra, but obviously this is a 1-to-1 ratio. So the formula here would be FeO, because 1 iron 2 will balance out 1 oxide, giving us something that is overall neutral. Now, if you're using the old crisscross method, that would give you Fe2O2. Well, is that wrong? It is. Because the subscripts in an ionic compound reference the ratio, we have to have the simplest ratio. So if you were using the crisscross method and you came up with that 2 and 2, you would have to simplify that, and hey, guess what you'd get? Oh yeah, FeO. Same as we got using algebra. Let's practice another one. Copper 1 oxide, write your ions. How do I know that this copper ion has a 1+ charge? Because it's copper 1. Oxide is almost always 2- with very, very few exceptions, and none that we'll ever cover at this level. So let's do our algebra. This, of course, gets us a 2 and a 1. Those will become our subscripts. Cu2O1, and of course we don't use the 1 because the fact that oxygen is written tells us that there is one of it. So our final answer for this is Cu2O. Let's do one more together. Nickel 4 chloride. So I know that nickel 4 has a 4 plus charge because it's called nickel 4. And I know that chloride ions are in group 17 and so tend to gain 1 electron, forming a Cl1 minus. I'm going to do my algebra. Okay, something times 4 equals something times 1. Well, obviously we would have a 1 and a 4 there, giving us subscripts of 1 on the nickel and 4 on the chloride. So NiCl4 is nickel 4 chloride. Are you feeling fairly confident on this? Well, let's turn it on its head. So I'm given a formula for Fe2O3. We know it's an iron oxide, but what we don't know is if it's iron 2 oxide or iron 3 oxide. Now, don't leap to any conclusions just yet. I'm going to start off by writing iron blank oxide. And I generally do that to remind myself that I have to use those parentheses with the charge number in Roman numerals, because if I don't leave myself a reminder like that, I'll probably screw it up. So let's examine the different ways to figure out which ion of iron we're dealing with. So I can write the algebra that I've been doing for finding formulas, and there's just one difference. I know that I have 2 of my irons, so 2 times some charge equals 3 times some other charge. Well, here's the nice bit. I know that oxygen generally forms a 2 minus. So this equals -6, and now it's pretty clear to see that this has to be 3. Yep, +6 equals +3. We're all balanced out. So what is this? Well, it's iron 3 oxide. Interestingly enough, iron 1 oxide, iron 2 oxide, and iron 3 oxide all have remarkably different characteristics. So it is really important to distinguish which ion we're looking at. Now, let's talk about how you would get to this point if you were using the older crisscross method. If you were using the older crisscross method, you would probably do something like what I used to call the reverse crisscross, where I know that I'm looking for a charge, a positive charge on my metal ion and a negative charge on my oxide, and I would take this 3, come up here, take this 2, come up here, getting a 3 and a 2. As long as this checks out, and 2 is in fact the charge that we usually see on oxygen, that would be fine, and we would know now that we have a 3 plus on iron, and this is iron 3 oxide. The crisscross method is fine as a quick shortcut as long as you know what underlies it. The place it breaks down is any formula that has had a ratio that was simplified. In those cases, doing the algebraic method doesn't lead to the same sorts of mistakes. So again, you're welcome to use either, but you need to understand the algebra behind finding these ratios. Let's try a couple more together. Okay, I've been given CuO. Well, I know that I'm looking for a charge on copper, and I'm looking for a charge on oxygen. Now the other thing I know is that I have 1 of each of these because there are no subscripts, and anytime there are no subscripts we assume that there is a single 1 of that ion. Well, if I use the algebraic method, I'm looking at something like this, and I know that 1 times the charge on the copper is going to equal 1 times the charge on the oxide ion. Well, I know that oxide ions are 2, so that gets me a -2, which means this has to be a +2. So I can go ahead and fill those in. What does this mean? It means I've got some copper 1 oxide. Now, if you were using the older crisscross method, which again doesn't allow you to understand what's going on, here's the problem you would run into. When you reverse crisscross those subscripts, you get copper 1, oxygen 1. And if you're not careful, you might forget, because it's not forcing you to think about the charge that oxide ions carry, you might forget to go, hey, wait a minute, that's been simplified. Oxygen isn't a 1, it's a 2, which would mean you would have to multiply the whole thing by 2. But with the crisscross, that's not as obvious. It's easier to miss, and it's easier to make a mistake. With the algebraic method, that doesn't happen because you have to fill in the charge on the oxide ion to have enough pieces of information to work with. Do you want to do one more together? Let's, and then get going on the practice and then the FIP quiz. Let's look at lead 4 oxide. So first, of course, we will write our ions, and then I'm going to do my algebraic approach here. Well, I can tell immediately that this is going to be a 2-to-1 relationship, and if I take 2 of these to 1 of these, sure enough, that gets me 4 plus equals 4 minus. The whole thing balances out, and my formula is PbO2. Now, if you were using the older crisscross method, let me show you what might happen. You would write all this, you would crisscross getting Pb2O4, and you might forget that you have to simplify coming up with PbO2. So doing this algebraically just avoids a whole bunch of mistakes. It's cleaner too. All right, do your practice, take your FIP quiz, come back for more.